I was going to talk about at Minos was some stuff about mazes, making mazes and so on. And I was kind of hoping that the audience there might be a bit wider and less experienced. So it's possible that you're not going to learn much new, although I'm pretty certain that, as they like to say on YouTube videos these days, if you stick through to the very end, there may be some surprises, because it's all about maximizing view time. Anyway, since we're predominantly about MicroMouse, we'll forget about line following and all of that kind of nonsense for the time being, and we'll consider just making a maze. And any of you who've tried to do so know that it's actually a little bit harder than you perhaps first expected. All of the parts have to fit just right, and that Goldilocks fit can be quite hard to achieve. In one sense, you don't want cumulative errors. In another sense, it doesn't really matter. You don't want them because clearly you don't really want the maze in the far corner to be a centimetre bigger than the maze in the bottom left-hand corner. But on the other hand, the mouse only ever sees one cell at a time, and so there's some kinds of errors that you can probably get away with. You have to be realistic in the accuracy that you can manage, and now that it's apparently so easy to buy very, very accurate laser cutters, maybe that's a problem that will start to go away. The other thing is if you're making things yourself, you have to be consistent. So if you make walls, you really don't want a wall that only fits in the bottom left corner of the maze and won't fit in this cell and is too big for that gap and too small for this gap. It drives you completely nuts. The Korean maze walls, for example, that were very, very popular because they were about the only ones you got, they had a dovetail slot, a dovetail tab. It's no good me waving my hands about, you can't see that. They had a dovetail tab in them and a dovetail slot in the posts, and if the gap was slightly too big, they just wouldn't go. It was horrible. And when you come in to do the holes in the base, they need to be perpendicular, because if your walls are if your posts are slanting off at one angle or another, then obviously it's going to be difficult to get the walls to sit right. Anyway, the moral of the story is think carefully about it, do it once, do it properly, do it right the first time. It's true for many things, but there's a lot of effort perhaps in making a maze, and you really don't want to mess about with it. I'll flip between full-size and half-size stuff here and there, but I happen to be fortunate enough to have several examples of half-size contest walls from different sources. And if you look just at the length, you'll see that the Japanese, the Chinese, and the newer style Japanese walls are all different sizes. They've got slightly different lengths. And if I use even the corresponding posts, I often find that unless I'm very, very careful, the Japanese walls just can be a little bit difficult to fit. You need to be very, very accurate to get the posts the right distance apart. So one style, the Chinese one, is what I've called the Chinese post is a universal recipient, right? So all of the contests walls kind of fit between them and work with those. And on the left, I've got some approximate, they look precise, but they're really fairly approximate dimensions. Anyway, the point of the story is the tolerances are worse than you think. If you've only got, an 83.2 millimeter wall, but and little tiny tabs, 1.4 millimeter tabs, and your posts are just 0.5 millimeter too far apart, they're going to fall out. It all gets to be a bit of a pain. Anyway, we'll come back to the walls and posts. Think for a minute about the base. And if you want to make a base at home, I was playing about, and this seems to be a convenient size in 1/2-inch MDF or plywood or something. This is probably a size that you can pick up ready cut at your local DIY place. And then the question is how to get the holes in and how to make sure that they are accurate and in the right place. And I did mine. I was thinking about how to accurately drill it and how to make it very, very nice. And then I just idly did a search for CNC routing on Google. And lo and behold, just 5 miles away is a guy who was advertising CNC routing services. And whilst I've not obviously searched for all of your locations, I would encourage you strongly to just try it. Just put in something like CNC routing or CNC machining and have a look at the Google results, and you may very well find that within a reasonable distance there is somebody who offers this as a service, or perhaps a makerspace that has a CNC router that can handle material this big. This was the largest size that my local guy could also fit on the table of his machine, so that's what I chose. But even if you only had like a 600 or a 610 by 610 piece, you'd still get a 6x6 maze, which is perfectly adequate for practicing. I took it up to him and he charged me 30 quid to route out the holes. They are all beautifully accurately placed, as you would expect. They are very well sized, and of course they're all perpendicular. And when I finished marking it up, I get a very nice practice maze. And I think 30 quid plus the material is not an unreasonable price compared to the pain of laying it all out, doing it yourself, and then living with the consequences of having screwed it up in some fashion. If you insist on doing it all by hand and you have access to a 3D printer, you might consider making some varied guides and jigs. You will need to measure carefully what your 3D printer really produces, because typically they're 1 or 2% out for one reason or another. So you need to make one, measure the exact distances, and then perhaps print out another one. The one on the right there, I put some steel bushes in. The one on the left, I can just push a nail through to mark the centers for the holes. If you use nails, by the way, note that the very point of an ordinary commercial nail is very unlikely to be concentric with the shaft, so watch out for that. And then on the one on the left is the one that I used to give me all of the nice layout markings that I have on my practice maze. So for a moment, let's just consider making posts. And if you foolishly decide to just make a 3D printed post and print it upright in the obvious orientation, that's what you'll get. And it's not a good idea. The lamination is perpendicular to the long axis of the post, and the peg will break off. I pretty much guarantee it. I ran the slicer for my printer, and to print one of these would take 42 minutes at 0.28mm layers. Now, bearing in mind that you need n+1 squared posts, where n is the number of cells, a full-size maze takes about 300 posts, and you can imagine that 42 minutes each, you would probably have run out of patience long before that's finished, even if you do them all at once. It's not a great idea. The other thing is that the peg part at the top is a critical diameter, has a critical diameter. And I'll mention it now in case I forget later, but I was emailing with Bernard a while back, and he concluded that it might be best to make a hexagonal or octagonal peg part, because that way you can make a better push fit inside a slightly off-sized hole, and then they'll tend not to rotate about, and the tolerances are a bit easier to deal with. But you may not have the same size post holes that other people have, and so an option is to print it with a hole instead of a post, and then you can put in an appropriately sized dowel. This is actually stronger in the end because the weak part is the peg part. I'm beginning to bluster now. But it still takes almost the exact same amount of time because the hole is almost as hard to print as the peg, strangely. Anyway, you all know by now that I think Bernard, forgive me if it was Bernard and others or just Bernard, you can correct me on the attribution later, but posts are much better printed, split in two halves and then joined together with CA glue or acetone if you're using ABS. And it's also quicker because of the vagaries of 3D printing. It's quicker to do the split part. And the only pain is you've got to glue them together, which is slightly tedious, but the benefits are well worth it. You will glue your fingers to them almost without question. For half-size posts, you can do the exact same thing. I print these at 0.2 millimeter layer height. I use PLA, so they're joined with CA glue, which is pretty quick and straightforward. And a pair of those takes 10 minutes. So for a practice maze, if I want 50 or 100, it's 6 or 8 hours print and the job's done. Note the details on here. This again is due to conversation with Bernard. Elephant's foot is a problem with 3D printing where the bottom squishes out. And whilst you can mitigate that in various ways, some people prefer to live with a bit just for better bed adhesion. But if you just clip the corners off at the bottom, which I think you can just about see, and if you clip off the sides of the peg part, then any elephant's foot won't make your print oversized or out of shape, and you get a very nice cut. By this point, if we had been at Minos, there would have been a big box of samples handed round. So you have to imagine that you're fondling those as we speak and seeing how it all looks and feels. So we'll move on to the walls, which are in some respects the more interesting part. If you were to try to 3D print classic walls, you would rapidly become very unhappy. Again, if you do the obvious thing and print them upright, on my printer settings, that's 160 minutes, nearly 3 hours for one wall. For a full-size maze, you need 300 of those. That would be 1,000 hours printing, which by my maths is, like 6 weeks worth. You're not going to do that, that's for sure. Plus, you only get 25 walls out of a reel of filament, so they're about £1 each. You might as well buy them. You might think to hollow the wall out. That actually takes longer, so don't do that. You do get a few more walls per reel, but it's still not a good idea. You might make the walls thinner to try and speed things up. That's not a bad idea, but now you're starting to talk about a fairly weak structure. You could, however, fill the void in the middle with foam board. So these walls are 0.8 millimeters thick. You could put 2 layers of 5 millimeter foam board in the middle to stiffen the whole thing up. But even so, at over 2 hours per wall, you'd have to be pretty keen to want to do that. The next most obvious thing to do is to print them on their side. You could print 2 sides and stick them together. That's worse. 226 minutes. Don't do that. You might shell that out to save yourself a little bit of time. That's still 155 minutes. Don't do that either. Right? So I'm just running through you may have thought of all sorts of ways to do this, and I sat down and I tried various ways and I timed them out just to save you the trouble. For classic, if you'd have no other means of making them, a method that perhaps has more merit than most is to make a frame. And the frame is sized so that the tabs at the end will just fit into the slots of the posts. So you could make that 2 millimeters thick. Then you could glue 2 pieces of 5 millimeter foam board either side to give you a total of 12 millimeter thickness. Slightly tedious to do, but it's not quite as easy as you might imagine to make the end caps, although we'll come back to that in a minute. 26 minutes for a half size, 21 minutes just for the frame, for the top. That's approaching reasonable. Get 200 of these from a reel of filament, and the result is stiff and lightweight. If you really want to make full-sized walls, classic walls, and you don't have access to power tools to cut material, give this some serious thought. It works quite well. Half size, of course, everything's half the size. The volume is 1/8, and so things start to get more reasonable. You can indeed print a perfectly good wall upright in one piece on your 3D printer. I have a fast setting, which is perfectly adequate, and I can do a single wall in 25 minutes. And that's how I print my walls. And again, you would have had some samples to show that this is actually quite reasonable approach. There is one noticeable downside, which I'll come back to in a minute, but there's no assembly, no messing about. The only thing that you might notice is that almost inevitably the bottom surface, which should become the top surface, will have a slight curve to it because the ends will lift as the material shrinks away from the bed. But the curvature, depending on your bed material, is going to be maybe 0.5 millimeter at each end. And honestly, you're just not going to notice. It's not a big deal. It may upset your purism, but it's not a big problem. The top surface will be dead flat, and that's the one which should go down on the maze base to avoid the wall rocking about. So a batch of 38 is enough for a 5x5 maze, and I just set it going and come back, and assuming everything sticks to the bed and doesn't result in one of those vast filament spiders, the job's done for a set of walls for a practice maze. And they're only 8 grams of material, so they're not terribly expensive either. Posts split in half. You can get a lot of posts on the bed of your printer, and 40 posts, which again is enough for a practice maze, 6.5 hours. They use 2 grams of material each, and they came out very nicely, which I would have hoped to show you. Now, if you don't have a 3D printer, or if you don't want to wait that long, or if you have other materials or other ideas, one of the things that you can do is to print just the end caps. Right. So for the classic maze, you might have 1/2-inch material MDF, 12 millimeter MDF, and you may have the ability to carve it up into the appropriate size pieces. But you still want those tabs to go into the posts, right? So one thing you can do, both for full size and for half size, is to just print the end caps. And if you've been paying attention, you'll notice that all of the ends of my maze walls have the little kind of tab bit not reaching the bottom on either side. And the reason for that is, A, it makes them slightly easier to actually put in to the posts, and B, if the post does not fully seat in the floor, you don't want that end tab bumping up against the bottom of the post and unable to go down to the ground, if that makes sense. So I find it easier to just have a little bit of a gap at either end, and then it always falls all the way down so that the wall itself sits on the floor and you don't get that annoying gap, which I see all too often otherwise. And the end caps are quite quick and easy. You can make the walls out of all sorts of materials. For half size, you can even cut 5 millimeter foam board and glue these on the end. And again, there would have been samples. I'll try and remember to bring them at the contest in the summer. And they work quite well. And they're very light and quite satisfactory to use. And the fact that you have a 5mm wall instead of a 6mm wall is really just, if you object to that, it's just fussiness. If any of you have a mouse that can detect the 0.5mm difference in distance to the wall, I'd like to see it, because I'd be very impressed. Right? As long as they're consistent, that difference in thickness isn't going to make a huge difference to performance. So just, I can pause there if anybody has any questions about the manufacture part of things. No? Okay. So what about the material? Again, this is mostly about half size and 3D printing of the parts, but those of you, if you've seen the walls made by Duncan and Bernard for the half-size contest, they're very nice walls. Okay, they have a very nice, flat, smooth surface. They're made by sandwiching two layers together, and you would have seen, in comparison to mine, they're most definitely superior items. But they cost a lot more in time and effort to make them that good. And I'm kind of idle, so I was looking at what you could do instead, right? And a question that often comes up is about the nature of the surface of the maze wall itself. And when people ask, they talk about maybe painting them, or what the finish should be like, what kind of paint, what kind of material it should be. And I have always said that really you want, a kind of matte white surface, such as you would get on white foam board, or such as you might get on just like printer paper, right? That's been one of my standards for ages. If you want a standard surface to test your sensors with, printer paper is it's pretty well uniform across different brands. So anyway, just bear that in mind. So if we have a look at some actual walls, and I set these up on a little rotary table, turn the wall in increments of 5 degrees or so, and measured the response using, I think they were Decimus 5 infrared sensors. And this is the response for different kinds of half-size walls under those circumstances. I forget the distance, it's not really relevant. You'll see that of the kinds that I have, they all have very similar responses. The shape of the response is quite similar. And the absolute reflectivity of the surface is also quite similar. The UK walls that we have, afterwards, tell me who's actually responsible for making them. If it's both of you, that's great. But the UK walls are a little bit more reflective than the other wall types that I have. And they have otherwise quite similar responses. If we normalize that, so we just make them all read 200, right, at an angle of incidence of 0 degrees, it's even more apparent that the UK walls are very close in characteristic to the current contest walls used in other countries. Now, you may not be traveling to other countries to do contests, but other countries may come here to do contests. And I've always felt that compatibility, as far as possible, is important. It would be absolute disaster for somebody to travel thousands of miles to attend a contest and discover that our walls are so different, they simply cannot make their mouse run. Equally, it would be terrible to travel a distance yourself and discover that you just can't run because you can't adjust the sensors. Doesn't matter what you do, nothing seems to work. And you might think that that's not such a big problem. You might think it's just about how bright the surface is, but it's not. When I print out several walls using a variety of different materials and run the same test, this is what I see. So the solid green is the UK ABS half-side walls, and the other materials there's a variety. Okay, so Rob kindly printed me some white resin walls. TO Pro White is Technology Outlet Professional PLA filament. I've used some foam board, and you'll see that they're not great, right? The results are normalised first. Don't get the idea that they actually all are as reflective as each other. The results are normalised, but the characteristic is completely different. And what you should notice from this is that the ABS walls, which remember have the same characteristics as commercial and international contest walls, are much more shiny. That is to say, the response is much more peaky around 0 degrees. All right? Significantly more peaky. And since foam board and paper are much the same, it turns out that my previous sort of standby advice of using paper or foam board as a substitute wall material is really pretty stupid, because they're just not going to behave the same. Okay, the off-axis, so your side sensors are probably pointing at maybe 30 degrees. The response is going to be way higher than a commercial wall, and the slope, which we'll mention in a minute, is also going to be dissimilar. So are there better wall surfaces? Well, there are, and again, these are normalised. So I've got two different filaments here. Sunlu White and G-Tech White are two of the PLA filaments. And also I've taken a wall and just put some vinyl sheet on it. This is the same kind that you'd put in a vinyl cutter or used by sign writers. And I think Duncan may have put some on the classic size walls as well. And again, that was at my suggestion, and it's not a bad suggestion, but it's not great. It's almost as good as you're going to get, but it's not fantastic. The material I've shown in the slide underneath, and I can send people details later, it's not terribly expensive. And it's a sort of semi-gloss, self-adhesive vinyl. It's very easy to use, very convenient, and it's got a response which is it's similar, is the best I can say. Right? It's the closest thing I have yet found. A slightly more glossy material would be better, but one of the reasons why I ask people to print me off samples is that it's quite expensive to just buy a reel of filament to print off two walls to find out how the material behaves. You might ask why the ABS walls behave so differently from the PLA walls anyway. Remember that my walls are printed upright, and so they will have the ridges on the walls, and the UK ABS walls are printed in pieces flat against the build plate on a cell Robox printer. And you might ask why I didn't do that if I wanted to replicate the performance. And the reason is twofold. One, it's really slow, and life's too short, and I'm too lazy. And the other is, it's all very well the Robox printer having a flat, smooth PEI print plate, but not all printers do. So, for example, my Creality Ender 3 by default came with a flexible textured print plate, which even with quite a shiny material has still got quite a rough texture to it, right? So it wouldn't matter if I printed them all flat, they still behave much the same. So after doing some experiments with that, it was just easier to print them upright, much, much quicker, and then compare the results. as a consequence. So anyway, based on these results so far, possibly the best or the simplest or the quickest way to, or the best compromise way to print half-size maze walls is to print them upright and stick sheets of vinyl sheeting on them for the finished surface. A quick word I mentioned about the slope at the sides, and I don't know if my mouse, yes it does, the mouse pointer just about shows up, but if your response is off here, so imagine the side sensors steering off the walls, and they're at somewhere between 20 and 30 degrees probably off axis, then a critical number that you need to bear in mind is this slope, because this slope is the steering gain of your mouse, right? So if R is the response, then dr by d theta, the change in response as a function of change in angle, is that slope there. So even if the response is down, if you can find a material that has a similar slope to that, then you're okay. And the GTEC white is kind of similar. The vinyl, there are errors in this, I need to repeat this. The vinyl sheet has a similar slope, but it's different, right? It's more sensitive, the slope is higher compared to the ABS walls. And so what I'm telling you is that not only would you need to think about the magnitude of the response when you're setting up your sensors, you would also need to think about the gain, the steering gain, which might be different from one set of walls to another. And if you're using a front sensor, and particularly with the simple UKMARS sensor board that's only got the one front sensor, this peakiness here is really important. The specular component of the reflection, you've only got to get less than 10 degrees off axis and you've lost 40% of your response with a proper, let's call them the proper walls, right? But if you're using some other material like the GTEC white, you've only lost maybe 10% of the response. And so that it's going to change very, very quickly with angle. And if you're a little bit off axis, your thresholds for wall detection and all sorts of things are just going to go down the tubes. So in some respects, this is the most important part of the talk, right? Trying to get, if you want to run in contest, either trying to get a wall that gives you a response similar to a contest wall, or thinking more about how you're going to adapt your mouse's response to different walls. This is really, really important. Much more so than you might think. And to be honest, until I did these tests, it's turned out to be much more important than I realized as well, and may or may not account for various shabby performances in the past. You've got to blame it on something, and this seems like a good candidate to me anyway. Right. So I took a UKMARSBOT, and I have a sensor board that's got two forward pointing sensors on it, not just one. So we're back to classic contest now. The walls that I used for this test are standard contest walls, but they have vinyl sheeting on them. I sat the mouse down in the middle and I had it spin through 360 degrees and recorded the sensor outputs. And this is with the common kind of very high intensity red emitters, you know, the kind that shine a little square with a hole in it out onto the wall, very, very bright. And this is the response. And what you should notice is, first off, the right sensor somehow has a sensitivity which is way, way down compared to the left sensor. And that it was closer to one wall than it was to the other. right? Now, why did I do this experiment? Well, I'm trying to think of ways of getting automatic calibration for the sensors. All of this testing it, putting in numbers and doing stuff is so tedious. I'm looking at ways of simply plopping the mouse down somewhere in the maze and have it run around and do some dancing and do its own calibration. So this was one of the tests that I did, and this was only the other day. Otherwise, you can see that the responses are quite nice, and they're just what you might expect. Okay, they're reasonably peaky. They have well-defined maxima mostly, and if you were to look carefully, you would see that the maxima are indeed 180 degrees apart, which is also very reassuring. If you take these sensor responses and you normalize them to the value of the peak, right? So the left one peaks at 900 and something, and you say, I want that to be some arbitrary value, say 128, and the right sensor, which is much smaller, but I normalize that to the same 128 positive. And then you plot them, and the green line is what you get by plotting the difference divided by the sum, right? Which is generally speaking, is your correct steering function for line followers, for wall followers, for all sorts of stuff. If you've got more than one sensor, it's the difference divided by the sum. And you'll see that reassuringly, I cheated because I've just shifted everything along by 5 degrees, because actually I started at 5 degrees off axis, but never mind. You'll see that you get a 0 at 90 degrees, you get a 0 at 270 degrees, you get a very nice, fairly linear steering range in between. So up to 15 or so degrees off that axis, you get good reliable steering, remembering these are the forward sensors, so you can align yourself against the wall ahead. You can be up to 15 degrees out, maybe even up to 30 degrees out, and still get a good steering function to allow you to align yourself to that wall if you normalize the sensors. Even at 180 degrees, which in this experiment is looking straight down a corridor with walls to either side, and the sensors at the front sensors are just picking up a little bit of residual stuff, you'll see that you still get a reasonable steering function. It's a bit noisy because the amplitudes are very low at that point, but actually as soon as you get a few degrees off axis, you get a good steering answer out of that as well. So you could probably get reasonable steering down a corridor just using the front sensors on this mouse. So this is the vinyl material that I mentioned before. And having done the experiments and thought about how that material is not shiny enough, I ordered a sample of some gloss vinyl, thinking I might find a slightly more shiny material. With the exact same robot, in the exact same setup, but with the walls this time covered in a gloss vinyl, this is what I get for the response. And that was a bit annoying. I mean, it's very shiny, okay? But if you have a look at the overall peak, right, the overall shape, it's not that much more shiny, right? It's not that much more peaky. But these peaks here, and here, and here, what on earth is going on there? I don't really have an answer. If I do the normalizing thing again, you'll see that you still get a reasonable steering function at 90 degrees. It's still, 0 at 90 and 0 at, well, pretty close to 270, but the gain is different because you're looking at the comparison of these peaky bits here and here. So the gain would be different, but you'd still get a 0, and you could still steer, albeit with some adjustment to the gain. So there's quite a lot there, and I seem to have banged on for quite a while, so I probably better stop and take any questions.
Any questions for Peter? Duncan?
The sensors that you use on UKMARSBOT, what's the reception angle of the photodiodes or phototransistors or whatever you're using?
If only I had prepared for this talk. I don't know.
Are they in sort of normal LED cases, or are they in a flat case?
Well, they're normal. I think they're SFH 409s, maybe.
So if they're narrow angle and you've got this small spot of light, I've got a suspicion that might explain your funny shaped curves.
Yes, I didn't want to preempt any discussion, but my suspicion is exactly that the sensor is off axis compared to the emitter, and because the emitter has these lobes to it, you're seeing the result of that off-axis behavior, and that would imply that a better detector would be one with a flatter, broader response. But I can't remember what on earth they are. Really, they could be SFH 309s. I should know, but unfortunately I built several of these, slung them all on, and never wrote down what I put in. And you know what it's like, as soon as they're out of the pack, they're just mysterious. But yes, and that's in spite of the fact that these are in little 3D printed guides, which, you know, they should be right on axis, but clearly not. I thought, I mean, I added all this on this afternoon because I thought this would be a kind of another valuable learn from my mistakes object lesson. Just slinging together bits and pieces and hoping that they'll make sense, as turns out to be more luck than judgment.
Well, after Minos, I've been looking at calibration as well. And it's a bit of a mystery, to be honest. I've been using a very simple approach. I don't think Peter, you're familiar with it, where you just start the robot against the wall and reverse it away. And I reverse it away from a cell with walls on both sides into an open cell where there are no walls on both sides, to try and see where you're picking up edges. And I can't report a great deal of success, if I'm honest with you. Stuff you think should be coming out the same does not come out that much the same.
The problem is that even under ideal circumstances, your walls mature at different rates and may not even come from the same batch. And my rule of thumb generally is that walls' reflectivity will change by 10%, up to 10% or so from cell to cell in the maze. And so if you, although the reversing and building a table kind of approach to calibration is good, it's true, generally speaking, only for that one wall. The process that I have in mind at the moment is to try and get an average over lots of cells. And this was leading to the idea that every time you do a U-turn, for example, you do a full 360 degree or actually a 540 degree turn, and record the maxima and minima as you go round. And the average, right, so when you're at 90 degrees and when you're at 270 degrees, the average of those two should be what you see when you're correctly centered, right? So you should be able to gradually build up a running average of the sensor response at that distance. And of course, if you're slightly off axis, as we've seen just now, that, depending on the nature of the wall, that can make a huge difference. So that's a pain. That's why rotating eliminates that. You can have a look at the point where you know that you're at 90 degrees. So that's one thing that you can do. The other is you really do need to calibrate against several walls, and I find the simplest way is to find a corridor and hold the wall against the hold the mouse back against the wall and use that as my reference distance, and just do that in lots of different places, and in my head kind of make a running average and make do with that, because everything else is hostage to fortune. The other approach, which I have running in UKMARSBOT at the moment, is slightly involved to describe. I'll do it briefly, and if anybody wants to talk about it another time, we can. But if you plonk the mouse down, right, this is for the side sensors, if you plonk the mouse down and let it run with steering down as long a corridor as you can manage, you need to just adjust the way your sensors work. So if your sensors are set up so that they can servo off just one side, say just the left-hand side, okay? Imagine that you're only using the left-hand sensor for guidance, and whatever the reading is when you start, that's your reference point, and you just run down, and it should stay parallel to that wall all the way down that corridor, regardless of what the values are. You don't care, right? But and all the time you go down there, you keep a running average. You just add up all of the values that you get and divide by the number of samples you've taken when you get to the end, and that's the average value that sensor has seen. Do the same recording the right-hand sensor. So now you've got two averages for the left and the right running down a corridor. You may have an offset, but you should be running in a pretty straight line if the walls are all similar. Everybody happy so far? Then, at the far end, you turn around through 180 degrees and you get a new reference. You can use either wall, it doesn't matter, but you get a new reference. And it's probably better to use the sensor that's now on the right, say, so you're using the same wall, so you've got the same track, and you run back down and you again keep a moving average or a running total, and then the average of all of the sensor readings. So you've got 4 average sensor readings. And the average, so you've got left going up, left coming back, right going up, right coming back. And within reason, the average of those two values is the average you would expect the mouse to see if it was censored all the way along the corridor. Yeah? And that way you have sampled as many cells as you can run along, 16 if you're lucky, 15 I should say, and you should have a good average of all of the walls down there by the time you come back. You can then save that as your average, and that works remarkably well.
It's 9 p.m.
Hi, Derek. Okay. Anybody got any more questions for Peter before we move on? Because calibrations are, I was going to say it's a dark art. I think it is a dark art, actually. But makes all the difference. My setting sets can be not very different on the surface, but have a very different behaviour as soon as you put the robot in a maze. It's quite amazing.
One of the problems you get is if you do a calibration like that, it's okay, A, for that wall, but B, at that particular angle. And as soon as you change the slight angle of the sensors to the wall, the whole calibration map can be completely different.
Yeah.
And of course, if you've got walls to the side, you're going to get some splashback off those, and that will change as you move about as well.
That's right.
It is. It's a pain. It's a complete pain to do, but.
Yeah. And your sensors are non-linear as well, so it's really once you get your angles off, you're in trouble. Okay, anybody else? Any questions before we move on?
Just a quick one for Pete. You mentioned that you've got a sensor board with 2 front sensors on it rather than the standard one. Is that available that we could get some made, or I could get some made or something.
I need to. I'm going away this week and running, and I'll tell you how well it performs. And if it performs all right, then I'll put it up. It seems to be okay, but there's a bit of an issue in terms of this is partly about the shortcomings of the AVR, about what order you light up the emitters and what order you read the detectors. Right, the emitters are in pairs, and what I have discovered also is, and you might all want to have a look at this, if you're using the current limited capacitor reservoir, right, to fire off your sensors, if you imagine that circuit that we use, a current limit resistor, and then you have a capacitor to store the charge, that capacitor is nowhere big enough. I don't know why. It was on my list of things to check, and I never did, right? So the suggested size of capacitor is just pathetically not big enough. And the problem is that when you fire off, if you've got more than one emitter, or even if you haven't, when you fire it off, that emitter immediately starts to pull charge out of the capacitor, and the voltage on it droops, right? So by the time you've read your third or fourth sensor, the emitter voltage has also drooped, and so it's less bright, and so the last reading, whichever one you read last, will have a smaller response than whichever one you read first, even if they're all pointed at the exact same surface. So really it needs some calculation doing, which I haven't bothered to do about that. And I can't remember what the specified size is, but the biggest one you can put on there is probably going to be a good idea. I've actually, on the mouse I'm taking with me next week, I've bridged out the current limit resistor and just sucked juice straight out of the 5 volts, because that's the only way to get a consistent emitter power. And that, I think, is why my right-hand side sensor is running at reduced power, because I think a software bug left a thing going at full throttle and damaged the emitter. So the capacitor is valuable. The capacitor reservoir is valuable for preventing exactly that kind of damage, but you need a much bigger capacitor, and I or somebody needs to do the sums properly to calculate what that should be.
Yeah, I'd forgotten we'd put that on. That's on the maze board, isn't it? I don't think it's on the line board. And we do only fire everything. You've only got one trigger, haven't you?
There's one trigger, and you fire off everything. And in my, you may be doing it differently, right? But in my code, all of the sensors are sampled with it off, and then they're all sampled with it on. That doesn't take long. It only if you're reading, but I read all the channels, so that's 6 lots of whatever it is. It's 120, 150 microseconds that the thing's on, and that's long enough to suck appreciable charge out of that capacitor.
Yeah, sure.
Your mic's off, Duncan. Still off.
I was commenting to Bernard that the A to D conversion time is important in this kind of thing. If you've got one of these ARM chips that does an A to D conversion in 2.5 microseconds, it's much less of a problem. But you also have to be wary about the charge time of the capacitor. Unless it's got something like 10 time constants, then the time at which you start sampling can be significant. If that gives you jitter, that'll give you jitter on your answers as well.
That's true. It's mostly important at the beginning when the capacitor is charging up. Once the thing has reached steady state, then the charge is reduced overall, and it'll kind of sawtooths, but it'll come to a steady state. It won't suck the charge out altogether. The rise time of the detectors is about 10 microseconds.
That steady state won't be steady unless the time between samples is consistent. So if there's a voltage change on the capacitor, depending on the time since it was last triggered, then that's going to come up as jitter on your readings.
it's potentially a problem, but I've
seen it.
measured it. I've observed it, and I've measured it on the scope, and it does reach an acceptable steady state once you've got the values right on the capacitors. On my main mouse, that's the method that I use, and I worried a lot about the discharge of that capacitor, but it does. You turn the sensors on, and after a fraction of a second, a fifth of a second, the whole thing's reached steady state, and you're good to go.
Well, it depends on how consistent your timing between sensings is. If your time jitter is, I don't know, 5 microseconds or something because you're using interrupt-driven things, it's probably not going to be a problem. If your time jitter is 500 microseconds, you want to start worrying about it.
Certainly, but I always run the sensors off an interrupt. They are pretty well rock solid.
Sure. Yeah. Okay.
I've got another point to make on this. There's something happens with the A to D conversion on some chips, because the ARM chip, I think, runs the A to D converter on some devices, runs the A to D converter off a different timer to the different clock to the processor. The A to D conversion time, there can be a jitter in that due to interaction between those two clocks. So it looks like some A to Ds are faster than others. I thought originally that was due to an interrupt happening during the A to D conversion, but it seems to be an interaction between the two clocks. So that change, when you're reading 15 A to D converters, or however many you've got, that puts jitter into the system as well. Because if the first A to D conversion took 10 microseconds sometimes and 15 microseconds other times because it didn't start at the right time, because the A to D converter clock wasn't in the right phase at the right time, then that's going to put noise on your signals.
These are all good concerns, and largely, I think, addressed by driving your A to D conversions off a solid interrupt timer, preferably with a high priority. And the kinds of jitter that you talk about, they're certainly there. And if you were in an environment where it was important, right? So if you were doing software-defined radio, or if you were doing an oscilloscope or something like that, these are certainly tunings that you want to consider, right? But given that, for example, even in Decimus, which belts around at a fair old speed, I throw away all but the top 8 bits of the response in any case, then 3 or 4 bits of jitter at the bottom, I honestly don't care about. They don't, compared to the other variations that exist, right? So if you log your A to D conversions, and even if you had your mouse running in a dead straight line, if you log what you see, I can show you later if you want, I've got graphs, against the walls, right? The environmental noise far exceeds the conversion errors.
Okay.
I've got no comment on that because I can't tell the difference.
Yeah, that's right. Okay. Peter, thank you. Peter lied to me about this. He said he'd be quick, but
I was quick.
But that's good, because everybody is affected by this, and as I say, the whole business of calibration. I don't know anybody who's got the golden bullet here, or the silver bullet that solves it all.